Right? Again, the basic thing is that if you start with a Lagrangian inside some symplectic manifold, we actually need like a couple more things like orientable and relatively spin. So we need this thing to give orientation to the moduli spaces we use. But today I'll like ignore every single sign, so we can also ignore this. Okay, so to this they associate, let's call it AL, like a filtered infinity algebra. And the problem that I want to talk about today is like, what can you say if the Lagrangian you take is just the product of two Lagrangians inside the product of two symplectic manifolds? Okay, so let's just review like how to construct this. So actually, I won't follow like the construction in foo. I will use like the theorem version because it seems better for these purposes. Mainly because it's unital instead of homotopically unital. Okay, so we start with Lagrangian. We take the theorem complex of the Lagrangian. We tensor it with this Novikov ring. And then maybe we have to complete this with respect to the filtration. And then we want, so this is already a DG algebra. Right, we have the usual differential and wedge. And now we want to put like more operations here. So what we do, we choose a complex structure, I guess almost complex structure. And then we look at this moduli space. So first we fix a class, relative homotopy class. And then we look at the moduli space of disks with boundary in L in class beta. So what this is maps from, I guess, a disk with k plus 1 marked points. I guess so. Boundary of sigma goes to ML, and the class of U is beta, and it's holomorphic. So then we have to actually compactify, so this could be not only one disk, but several disks and spheres. And then, I guess, this thing comes with like some maps. You can evaluate at marked points. So you go from here to L, so from I from 0 to K. And then, to define these operations, so now I have to lie a little bit. It's not entirely true, but what you do, so you take some K forms here, K differential forms, and then you pull them back here using these evaluations at marked points. Then you edge all of them. And then you kind of integrate along the fiber of evaluating at the 0 marked point. Okay? So actually, I mean, to do this, you need this to be like a smooth thing, and like this evaluation to be always a submersion. So to make actually this work, you need all these Kuranishi neighborhoods and do a lot of work, but let's ignore this for now. So then we put all of these together, and we define this operation here on that space after tensoring with the Novikov ring. So you just add over all betas that have holomorphic representatives, and then you put some parameter T of the Novikov ring. So here you put the energy, and then you also put the Maslov index. Okay, and so this is like very brief review of what they do. And so now this gives an A infinity algebra, so I guess it's a theorem. So we get an I guess filtered A infinity algebra. And let's call it AL on this thing, like the RAM complex tensor with the Novikov ring with these operations form an infinity algebra, and it's actually unital. So that's like a big advantage for our problem that I'll discuss later. So the unital is the usual unit, just constant function equal to 1. And so just a reminder, what's a unit in an infinity algebra? It just means that if you have 1 appears in one of these mk's, this is 0, except when k is 2, where it is a unit. So this x, of course there are minus signs around here, but let's ignore that. So now the problem that I want to discuss is if you take two symplectic manifolds, one Lagrangian in each manifold, what can you say about this guy, the product of the two Lagrangians? If we ignore all these other operations, like everybody knows what this is, right? So the theorem complex, this is just the tensor product of these guys. It's just Kunneth theorem. We even know what the map is. You just take these two forms, you pull them back to the product, and you wedge them.
Maybe in completion.
Oh yeah, here I'm just looking at before putting all the rest. Okay, if you tensor, then you have to take the completion. Okay, but now we want to see what happens when you put all these other operations. And to do that, we first have, if we assume that this should be true, so here we need like to discuss what this tensor product of infinity algebras should be, of filtered infinity algebras should be. Okay, so now I'll have to discuss that. So actually I think people started thinking about this problem of taking tensor products of infinity algebras long time before people thought about this kind of thing that I want to talk about today. And so the problem is just take two infinity algebras. Okay, and just let's ignore all these Novikov rings, just two infinity algebras with no M0, so the classical infinity algebras. How do you make this tensor product, right, just of the vector spaces, into an infinity algebra? Okay, so this was answered. I think the first people to answer this was, now I'm going to mispronounce the names of these people. I apologize for that. Saneblids, sorry about this, and Humble. I think they are from Georgia, that's why they have complicated names. And so the way they do this, they think about this in like terms of operads. So an infinity algebra is a module over the infinity operad. So to answer this question, you have to, let's call, so the infinity operad. So this is just the cellular chain complex of the Stashev polytope. So, and so this is the moduli space of disks with n marked points, or n plus 1. And then you take the cellular chain complex of that, and this is indexed by trees, planar trees, like rooted trees. Okay, so if you think on this in these terms, the only thing you have to do is find the diagonal of this operad. So find an operad map from here to the tensor product with itself. So, of course, I mean, there's like an obvious map would be to take like the map induced by the diagonal on the level of the spaces, but the problem is that this map is not cellular. So we need to find some cellular approximation of this. And that's what they do. Actually, more people did this. So Markle and Schneider later did this. Lode also did this. And so we have like at least 3 different diagonals. And they should be all exactly the same. But no one has actually proved that, because it becomes complicated after a while. So I'll just write down what the answer is. So of course M1 in the tensor product. So this part just generalizes tensor product of DG algebras. So this is just one, so identity tensor M1 plus M1 tensor identity. M2 is just tensor product of this. So this so far is just tensor product of DG algebras, nothing new about this. So M3 it starts to get interesting. So now I'll use trees to denote the operations. By some reason my trees are upside down, so okay, so what I mean by this is that on the left side you apply M2 to the first two guys and then take the result, apply M2, here apply directly M3. So this is what it means. So this is what M3 is. Just going to write M4 just because it's fun. And so you have an idea how like fast this grows. So this is one term, the other term is this. Of course this has a lot of signs, but I'll ignore them. So now this is starting to get boring. Okay, so it's 6 terms. So when you get to M5, you already have like 20-something terms. So I guess that's why no one has actually proved that all these diagonals agree, because combinatorial is kind of hard problem to do. Okay, so now I'm just going to look at a different approach you can use to try to define tensor product of infinity algebras. And this was proposed by Kontsevich and Soibelman, and it's kind of very different, at least apparently. So what they say is that the tensor product, A infinity tensor product of two A infinity algebras should not be the tensor product of the vector spaces, but should be this. Okay, so what you do is, so the vector space A tensor B is naturally an AB A infinity bimodule. Okay, so once you know that, you look at endomorphisms of this bimodule. And that's what this thing should be. That's their definition. And notice that this is just a DG algebra, not a infinity algebra. So it doesn't have either MKs, just M1 and M2. Okay, so actually this looks very different, but it's not as different as it looks. So what you can do to compare them is like use some perturbation lemma, homological perturbation. So what you do is the following. So you look at this vector space as a chain complex, only looking at M1s, forgetting the rest, and you can include that inside there, that thing. Okay, kind of like what you do with just algebras. You take an element here and you multiply on the right the guy on A and on the left the guy on B. Okay, so you do a similar thing. So you have a map there. And now, if you assume that A and B are unital, we can like write down the map going that way, which is you take an endomorphism and you evaluate it at 1 tensor 1. And you get a map back. And now, if you choose here the like right homotopy between the identity and this composition, so I guess I compose with P, and you use this perturbation lemma, so this will allow you to take this DG structure here, pull it back here, but here it will appear as an A infinity algebra, so higher MKs will show up, and it should be true that these things agree. So applying homological perturbation, the answer should agree with, like, I'm going to put should because I don't actually know how to prove this. Is the same problem. Like in the beginning they agree, but after a while it becomes too complicated combinatorially to actually prove, but I'm very convinced they actually agree with previous definition. Okay, so now this approach has one advantage.
Is there some universal property that the tensor product says?
I don't know. It should be, but I haven't seen anyone like thinking on this problem anywhere, so I don't know. There should be, because clearly there are like a lot of different definitions and they all turn out to come out the same, so there should be kind of essentially the right way, so some kind of universal property, but I don't know.
The problem is that this construction is not factorial. Right? You cannot solve out how to do morphism with a different problem.
So you cannot what?
I mean, you have a morphism from A to A prime.
I see.
Then it is n morphism, so there's no map.
Yeah, so I think the same guys, Sane, Blitzy, and Humble, they also do a diagonal of the multiplyhedron. So maybe that would like allow you to get some kind of functoriality, because the multiplyhedron rules a infinity map. So maybe from there, but I don't know. It seems complicated because this is not easy to deal with all these terms. So remember, what we wanted to do was take tensor product of infinity algebras, but filter the infinity algebras, so stuff with M0 and all of that. So the advantage of this approach is that you can do all of this if you assume that A and B are filter the infinity algebras only. So you can carry out all this construction. There are like several things that go wrong, but in the end everything turns out okay. So the thing is, and this is, I don't know, at least I find it surprising the first time I saw this, if A and B have M0, so A infinity algebras with M0, this tensor product is not a bimodule over AB. So, I mean, this actually doesn't make sense, but if you carry on with this thing, it turns out that in the end, you still get something here, and this is a DG algebra, but now with M0, so a curved DG algebra. So you do the same thing, the exact same construction, and since we are working with this gapped filter, the infinity algebras, we also have a homological perturbation lemma for this case, and it turns out that what you get is the following. So for M0, maybe I should write it here. For M0 on the tensor product, what you get is just one tensor M0 plus M0 tensor 1. And the rest is the same formulas showed up before. If these things are unital, strictly unital. If they are just homotopically unital, I think you can do the same thing, and I even found this homotopy here, but then like the formulas are a complete mess. They don't make any sense at all. So that's why I'm using the RAM version, because things are unital from the beginning, so it should be okay.
Can you define in the inner forms the category of A infinity algebras?
Inner Holmes?
Yeah, form has like very good algebra structure.
Yeah, I don't know.
I mean, literally, like, you want some kind of tensor to absorb the inner forms.
So you mean like tensor plotting having some kind of property with Holmes, like this adjoint? Yeah, I have no idea. I mean, that would be some kind of universal property that you use to define tensor product, but I don't know that, and I haven't seen that anywhere, so I don't know if anyone has done that. I don't think so.
So without differential, we do have the kind of here, like if we forget about the differential, then we do have that adjunction.
We have?
Yeah. So when you forget about the differential stuff.
Okay, maybe, I don't know. I would be happy to learn about that, but I really don't know how to do that. So, actually, like our construction, the infinity algebras are gapped. So we can like break out these M0 and M1s in the gap. Remember, like all our operations were indexed by this guy in relative pi 2. So actually you can break down what is M0, and now say like beta 1 cross beta 2. Like if A is G1 gapped and B is G2 gapped, like tensor product somehow is the G1 times G2 gapped. So these things are indexed like this. So what this is 0 if beta 1 and beta 2 are both non-zero, and it's one tensor M0 beta 2 if beta 1 is 0 and the symmetric. And the same thing for M1. In the higher ones, no, you just add over all possible ways of splitting the betas on each side. Okay, so now let's go back to the problem we wanted. So remember, we have this thing, this infinity algebra that we get L1 cross L2, and here on this side we have this tensor product that now we know what it means. So at least we have a definition here. So we can try to prove that these guys are like homotopy equivalent or something like that. So for that purpose, it seems reasonable to consider like something here in between and this something. So the complex is just again just the RAM complex of the product, again tensored with this Novikov ring, but these operations that I'll put here will be slightly different. So the moduli spaces I will use here, so let's call them mk plus 1 tilde beta 1 cross beta 2. So what these things are is, okay, so let's again say k is greater or equal than 2. So what I do, I take holomorphic this with k plus 1 marked points on each separate component. So this guy with boundary in L1, this one with boundary in L2 and class beta 2. Again, k plus 1 marked points. And then, we take the fiber product over the moduli space of k plus 1 of disks with k plus 1 marked points. So we look at pairs of stable maps whose domain agrees. This, if you think about it and you take in definition of this one like a product complex structure, this seems that this moduli space is almost the same to the one we used, but it's not quite. So actually how to go from here to here, I'm not like entirely sure how to do it, but I have some ideas. So here we use this definition, and when k is either 1 or 0, it's a little different. So we have to do similar thing there. So if beta 1 is 0, we use as moduli space L1 cross this mk plus 1 of L2 class beta 2. And the symmetric situation when B2 is 0, and when they are both non-zero, we don't put any moduli space. And so using the same definition as before, that correspondence we did before, like pulling back at the marked points and integrating over the fiber, but now using these other moduli spaces, we still get an A infinity algebra beta. Okay, and it seems somehow to be in between. So from here to here, I don't think I'll say much about how to go from here to there, but here I kind of can say something. So the map going from there to there, so let's call it phi. So we know what phi1 should be, right? It's the same map we use to prove the usual Kunneth theorem. You just pull them back and wedge them. So you pull back the forms and you wedge them. So that should be that map over there. And now we have to compare what happened to these other operations. So if you look at this definition here, and if you remember the definition of the tensor product, you'll see that via this map that I wrote over there, like these two guys here have the same M0, the same M1, and the same M2. Okay, so when you try to construct an infinity map going from one to the other, this is the only phi1 you need, and you can actually take phi2 equals 0, because like M2 is the same on both sides, it agrees. So the problem comes when you try to compare M3 on both of them. So if you remember, probably shouldn't have erased that. So M3 on the tensor product was something like this. Right? And here I use, remember in this definition, I use pair of holomorphic curves that have the same domain. So now let's look at the picture of M4. So the moduli space with 4 marked points is just an interval. Okay, so this is just like 0, 1. So we can actually make a picture of this. So let's say this thing. So and those are the trees indexing the different cells. So now we take the product of two of these guys. And if you look at it, in the M3, in the tensor product, we are counting curves that lie here. Right? So this one is this guy tensor that one. And this one over there is this guy tensor the other one. Okay? And on the B, in this infinity algebra that I wrote there, we are counting things on the diagonal. So the difference here we count curves that lie here, whose domains lie here. We count pairs of curves whose domain lie there. So if you want to compare them, you can look at curves whose domain lies here, in this triangle, and this will give an homotopy from this one to this thing over here. Okay? So let's call this guy, I don't know, f k plus 1. Okay? And now, I don't have a good description of this guy in higher dimensions, and I more or less know what it should be. But, so the idea is that this fk plus 1 should be, what dimension of this? K minus 1, I guess. So this should be dimension k minus 1. Should be some submanifold, not exactly, but almost, of this product of two moduli spaces of this with k plus 1 marked points. And so what are the properties this thing should satisfy? Should be smooth, and not exactly, but I mean, I don't think this will ever be smooth because on the boundary you have like non-simplicial corners. So, but other than that, it should be smooth. And the boundary of this thing should be, one of the boundaries should always be the diagonal. The other boundaries should be all these things that appear on that thing, on the definition of mk in the tensor product. So the sum of all these guys. And there should be some other stuff there which correspond to the other terms in the A infinity map equation. So things of this form, phi I mj. Okay, so in higher dimensions I don't have like a good description. I can make the picture of the higher dimensional one. It's kind of strange, but this thing has to exist because this thing is just a polytope, so it's homotopically it's trivial, and if you add all these things, this gives you a closed chain, so it must be the boundary of something, and that something should be this fk plus 1. And I mean, actually like one more condition that this fk plus 1 must satisfy, which is you should have some kind of forgetful map, forgetting the ith marked point. And there's like some condition on what the fiber of this thing should be to deal with M0. But if we can do that, then we can define this phi k beta 1 cross beta 2, the same thing as before. So counting those curves. So yeah, let's just say it like this. So you look at these pairs of curves whose domain lies in this fk plus 1. And now we count curves as before, so we pull back forms and push forward at the 0 marked point, and that should give you phi k, and should prove this is, I mean, once we have the A infinity map, we know it's a quasi-isomorphism, because it is already an isomorphism just on cohomology of like just the usual differential. So that should like take care of the one part of this isomorphism that we want. The other part, it's kind of more technical, so I probably won't say much about it. But so if you think about it, the way I define, so on one side, I'll just say briefly, like one remark, like before. So on B, if you remember, like we define this as pairs of curves with boundary on the two Lagrangians, whose domain is the same. Right? Will lie when you forget the maps and just keep the domains, they are the same. So this is not exactly this guy here. So this is only the same if the domains are stable already. Like without the map, the domains are stable. These things are locally isomorphism. But near the boundary where you have unstable components, these guys differ. So you have to find, I guess, some coordinate from here to here that collapses that part of the thing. And that part shouldn't have any interference with the result. Because when you look at a map that is like unstable, so you don't have enough marked points, and you take a map here and you project it to this product, and now we don't have this thing, doesn't exist for k less than 2. This guy here, if both beta 1 and beta 2 are non-zero, this guy here has smaller dimension than this one. And all the evaluations map factor through here. So those things shouldn't really matter. So we should really be able to find a coordinate from here to here that collapses those boundary components and gives that other part of the isomorphism. Okay, but I'll stop here. Thank you for listening.